Welcome, CppIndiaCon. This is very exciting. So we'll go ahead and dive into it, and I'll look forward to chatting with you folks in the Q&A session on Discord as well after if you have questions. I'll also keep an eye on the chat too if there's any clarifying questions that you folks have. So feel free to engage. This should be interactive. This should be fun. This is CppIndiaCon here. So with that said, I'm going to be talking about optimization design patterns. And this is sort of towards an introductory audience. So I'll help you along if you're not an expert, but even if you are an expert, I think you'll get some things out of this. But as I was thinking about this particular topic and thinking about design patterns, as was referred to, we often think about things like creational, behavioral, structural, or maybe other types of architectural design patterns. But what I really found is this just kind of boiled down to optimization strategies. And these are many things that I think some of us know, but I want to help kind of tease out what some of these patterns or strategies are in our code so that we can write more efficient C++, better performant, or just really try to understand, if we are writing better code. So anyways, with that introduction, I got my little introduction already, which was very great. So I love teaching, and I also do some industry stuff in graphics and performance, as mentioned. The code for this talk, if you folks do want to check it out, it is available here. If you want to play with any of the examples and refer to anything, feel free to grab that as you please. So here's the abstract that brought you to the talk. Hopefully, that's what you'll get here. But what I really want to start with here is a little interactive exercise. So feel free to type in the chat. And I wonder, you can type yes or no, if how many of you folks have heard this phrase or this quote before. Okay, so get ready to type in a Y or an N here. And here's the phrase. It's from a very famous computer scientist who's a professor. He says, premature optimization is the root of all evil, or at least most of it in programming. And wow, the chat is moving very, very fast. I see many, many Ys here. So many folks have heard this. Not everybody, though, which is OK. So that's why I want to introduce this to you. So let's say that's, I don't know, of our many participants here, at least 80%, maybe more there. I've heard this quote before. But pushing this just a little bit forward here, for those of you who have heard this quote, how many of you, and again, you can answer yes or no in the chat, have actually read this in Knuth's paper for which this quote's attributed? Yeah, for a long time, me too. It was a no. Something you read on advice, Stack Overflow, a forum, someone tells you. And the advice means well, but we need the full picture here. I love that someone's saying not yet, because I am actually going to show you the text here so that you can all read it and just have a little more understanding or context of where this comes from. So the original paper that Donald Knuth wrote is filled with lots of these gems. Premature optimization is the root of all evil. That is a sentence from the original paper, Structured Programming with Go-To Statements. So go-to statements, something from long ago here that we usually don't write in our programs. But there is much more to this paper here. Okay, so the other parts to it, the very following sentence here says, yet we should not pass up on our opportunities in that critical 3%. So again, this idea of folks taking this quote and maybe extrapolating or interpreting it as never optimize your code, that's not quite right? Because we have maybe some percentage of our code where we can improve and make faster, okay? But there's still yet more wisdom in this work. Again, this paper by now is well over 50 years old, but still wisdom that applies to us programmers today. And he goes on to later say, it's often a mistake to make a priori judgment about what parts of a program are really critical. So again, making a judgment without measuring is what he's saying. Since the universal experience of programmers who have been using measurement tools has been that their intuition or intuitive guesses fail. So again, often we might say, hey, that code's going to be fast. We type it in and say, hey, it looks fast after we run it, but we have to measure it, right, to understand fully. So with that in mind, this idea of premature optimization is the root of all evil. But as I like to paraphrase, and I've heard others, but never optimizing when there is an opportunity available, that's also evil. Because we should be writing good software for our customers, because that's what C++ allows us to do, to write fast code and have control over the performance that we get through this language. So with that said, again, Knuth is never saying never to optimize, just to optimize responsibly and make sure that we find the right pieces to optimize in our code. So what we're finding here is, or what we're going to find out is optimization can be a little bit of a tricky story. So I'm going to give some examples to this, and again, some strategies that we can employ in our code to hopefully, again, give you some patterns or things to look at for. So again, from Knuth, some more quotes here. This idea that there's a little bit of a tension sometimes with when we write programs that are supposed to be very optimized. What do I mean by this? Well, sometimes writing really performant code might result in us transforming or writing our code in a way that's less readable, maybe less understandable. Now, I'll argue if we learn some of these patterns, we can understand what the intent of the programmer is doing, right? Just as we learn more. But there is a little bit of a tension here. So what we really, optimization in our code might result in us making some other trade-offs beyond time and space, which is what we're going to talk about, because that's what we often trade to get performance. But sometimes we're also considering readability, maintainability, or the correctness and precision. And some of that's just about learning, again, what these patterns are, or these different strategies. So there is also this other tension that's interesting, and maybe you've seen some other great C++ talks that talk about this, but sometimes the simplest code is actually the most optimized because it's very predictable. And we're going to look at some optimizations that maybe your compiler can actually infer or do something very optimal with, because it is just very simple code. It's very predictable with how we can handle it. So I'll go ahead and demonstrate a few patterns. They might obfuscate the code a little bit to make it hard to read, but maybe they're interesting enough or simple enough that you need to learn about them because they'll help your code in some way. Or maybe these are things that your compiler is doing for you anyways, and you just want to understand what they are. Okay, so let's go ahead and get an introduction to some of these strategies. Now, what I will say is this talk's not going to cover the CPU, your hard drive, general architecture, but there have been lots and lots of great C++ talks on that. So I've referenced a few here from some folks that I think are quite good. And I think there's going to be some great talks addressing some of these issues as well at CppIndiaCon as well. So you'll want to listen to all those talks as well. And another great area to look at for different optimization strategies, which we're going to find out, is, again, general compiler optimizations. Because compilers really, or compiler implementers who design our tools like GCC, Clang, Microsoft Visual Studio, they look at these patterns and figure out, well, what can we automate here? Where can we make some trade-offs that might give us performance? So again, that's a reason to be aware of some of these different tricks we can do with our code or these different strategies. All right, so getting into our goals here with that introduction, again, hopefully I'm going to just show you a little bit of a grab bag of different strategies here. Okay, so let's go ahead and get into it. And I am going to show you a few benchmark numbers. And any time you see benchmark numbers or performance, I would encourage you to download my code and see if you replicate it. I think that's just a good thing to do as a scientist to make sure, on your particular machine, your platform, you're getting similar results. But this is going to be a fun talk for everyone regardless. So let's go ahead and get into these strategies here. So again, when we learn about patterns, whether they're things like the design patterns, again, they're sort of recipes or blueprints. Um, we could probably formalize them in some other way. And I'm not going to as much be looking at bit hacks like I'm showing here. Like maybe some of you folks know, like I can use the shift operators versus times equals 2. These are some things that our compilers are good at and knowing about, but I want to talk a little bit higher level here. I want to talk about this trade-off of space or memory versus time, how much time it takes to compute something. So I'll go ahead and summarize a bunch of these techniques. I'll run through as many as we reasonably can, and then we'll look at a case study of just how to sort of measure and apply some of these optimizations. And where these come from, if you really want to do a deep study, there's a really nice book, again, taking us back in time a little bit here, written by John Bentley. It's called The Rules of Performance, or these are his rules of performance in the book, Writing Efficient Programs. So there's a whole bunch of these rules written, again, many years ago that still apply today. So that's what I'm going to borrow a few of them for. And again, we have the classic trade-offs when it comes to our data structures that you might learn about: space for time, time for space, and sometimes you can get space and time both at the same time. Okay, and really, what this is all about, computer science, in my opinion, especially when we talk about performance, which is one of my favorite topics, is just understanding the trade-offs here. Okay, all right. And I have some comments. Someone has actually read this book at 40 pages. Excellent. So you'll be familiar with at least some of these first few ones. But let's go ahead and start off with the first ones here, talking about modifying our data, space for time. This is sort of a classic, a good warm-up I think folks will know about. But looking at these two structures here, so drawing your attention to the top right, I have a singly linked list. I can get to the head of this data and then move to the next node. Okay, we do this as an exercise early on. But if I want to append something at the end, again, that means walking through this entire list here, okay, which of course takes a linear amount of time depending on how large that collection is. So I can speed this up by just trading a little bit of space, adding a tail node here that points to the end, and we do a little bit of extra bookkeeping here, and append operation becomes constant time. Okay, so that's an example of the type of trade-offs we might be looking at or thinking about in our computation. So it's a small memory cost overall for maintaining one additional pointer where we can get more performance. So the next that I'll talk about here is within that same idea here, still space for time. So again, another classic example here, computing something, some Fibonacci sequence. And this holds in general if you're going to compute or maybe recompute some result. Maybe you're writing a game, for instance, that has to compute some score or some result in a table. So what ends up happening with this particular algorithm is if you kind of draw out the shape of what it takes to compute this Fibonacci sequence, you end up doing a lot of work, especially with this sort of recursive pattern here I'm looking at line 10. I'm sort of computing the 6th number. Well, to get to that, I need the 4th number and the 5th number, and to get the 4th number, you need, the 3rd and the 2nd on this side and the 5th one. So you're repeating a lot of this work, right? This is a 2 to the n algorithm here. So this particular program, if I run it to compute the 45th Fibonacci number, it takes 9 seconds here. Okay, that would be unacceptable in my book. But if I didn't know any better or think about some strategy, maybe I would just move on. So we can speed this up again by doing the same trade-off, space for time, and storing. And we could do something like this at line 6, just store all of the results of our first Fibonacci number, second, third, fourth, etc., in a table. So this, again, for those of you who know, would be a memoization strategy. But all we're doing here is allocating some extra memory to store our results. And if we do this such that in this particular code sample here at lines 20, 21, and 22, we're just looking up a value first before doing a bunch of work, sort of similar to that linked list example where we just look to the tail right away. Well, the actual performance for this program is 0.002 seconds for the same computation of the 45th Fibonacci number. Now, again, your results might vary, but I would argue that's a really good trade-off. So as someone says, yeah, dynamic programming to save the day. And this is the kind of strategies that we want to employ. Okay. So when it comes to this same sort of trade-offs, time or space to save time, we also have some other ways that we can modify our data for a time for space trade-off. So these are things like packing and compression. Again, things that we probably use often, but if you're not writing these algorithms, you might not think about. But let's say we are now working with a bunch of data and we want to reduce the space here. So we can use things like a zip algorithm or RAR, or whatever compression that you want to do to actually reduce the amount of data that you're working with. Okay. And then that trade-off is, well, it takes some time to unpack that data again and to use it. But you get that advantage of if you're passing or moving that data around, it's less memory here. Okay. So this is applicable if you're, again, transferring files over a network or packets in a network application. So all these different things that we can do. And again, some of these other practical tips are just things like using smaller data sizes. So again, if our range of some data is only 0 to 255, like let's say we're storing dates of the year on most calendars, say the month, we might be able to use a smaller data type versus just making everything an integer. And these things tend to add up over time if you're working with pixel data and so on. So these also show up in other sort of applications at a higher level architecture. Again, these same trade-offs that we think about sometimes in our code, even are things like, why would we use another language like, dare I say another language here, Python? That's CppIndiaCon, but I know some of you are using it. But it is an interpreted language, right? And we do this sort of trade-off of, well, just being able to execute our code without having to rebuild it. And that's a different type of trade-off that we might make, right? To the sort of time for space here. So again, these are just other sort of examples where these things show up. So let's take a little bit more look at some of these space and time trade-offs here with just for these things that come up in our code. So again, let's say that we have something like that calendar example. So drawing your attention on the left side here, where I need to store a year, a month, and a day. Well, these are all 4 bytes for my architecture here for the year, month, and day. So that's going to be 32 bits. That's about 96 bits of information here just to store a date. And if we're storing lots of dates, maybe in a database, for instance, or you can imagine on Facebook or something, on the LinkedIn CppIndiaCon page where there's just lots of posts, that could add up to be a significant number. So is there a way we could compress that down? Well, there is in C++, right? We can actually use bit packing to actually say, well, for our year, we only need, say, 13 bits, okay? Actually, I think we'll probably need more. I think we'll go more than 8,000 years. But you see that we can actually use only the bits that we need in a particular type here, like an integer, for, say, the month here. If we only need to store up to 16 months, again, there's different calendars, but that might be sufficient for us, or only up to, say, 32 days here. So at this point, we're down to 22 bits in this bit pack structure here. And some of you might also catch that there are some padding things that we have to do. So let's just call it maybe 32 bits or so of information here. But that's much better than the 96 bits. Again, as you store lots of information, these things matter, or on mobile devices. So there's my little caveat on, yeah, it might actually also take you some time on some architectures to sort of decode what 22 bits means. So the story, again, this is why we're going to have to measure in a moment to figure out, is this faster? So sometimes, though, we've looked at some trading space for time, some time for space trade-offs. Sometimes you can get both. Sometimes you can get space and time. And this is where parallelization comes up, which is going to be something that folks talk about later. But specifically, SIMD instructions, which are something that might be of interest for folks is where you can execute a single operation on multiple pieces of data. So that should save you time if you're able to do something in parallel, for instance, and potentially also space, less temporary variables that you're setting up to compute and registers and these types of things. So sometimes you can get a win-win as well. All right, so let's look a little bit at modifying the code structure, because this part previously is a little bit about, if I go back to, let me go back to Bentley's rules here, sort of time for space. But you'll notice a lot of the rules here actually have to do with modifying the code structure, where we can get some performance. So let's look and see what that means here. And these are some different trade-offs that we can make that oftentimes our compiler will help us out for. So these are just generally useful to know. But again, if you want to ensure that these things happen in your code, if you really need some performance, then again, these are worth knowing, just explicitly doing exactly what you want. So let's go ahead and start with loops, because that's one of the main places where we could optimize our code. Because oftentimes when we write programs, well, that's where we spend a lot of our time. We're looping and looping through data, looking through our different container data structures. So I'll show just a few different optimizations we can do with loops that I think are fun. And again, our compilers are pretty good at some of these for us, but sometimes we will want to be explicit. So here's just a tiny example. On the left side, what I'm doing here is I've got a loop structure here, lines 13 through 16. And what I'm doing is I'm calling this function here, approximate pi, right? Roughly 22 divided by 7. Now, why I wouldn't have this in just define, or even better in C++, actually look up the or bring in the actual const expr value. I just needed to demonstrate some work, but I'm doing this work over and over and over again. 2 times approximation of pi times I here, right? Computing a bunch of circumferences. So I could actually lift out that work, right? This part here, the 2 times the approximation of pi, out of the loop here, right? Just compute that one time. And then I could, every time this loop, be doing less work. And that's the idea of code motion, this optimization, okay? And someone is commenting here, the compiler would optimize it anyway. Probably, right? That's probably true. But some things that we might want to keep in mind are, well, if we write it in this way in the first place, it's again explicit that this will happen. And sometimes it's just a little bit less of a mystery if we're doing, say, a debug build, for instance, because maybe our debug build doesn't do all the optimizations as our actual release build, which is moving our code around a bit. So again, sometimes it's just nice to be really explicit about this. Okay, and we can actually improve this piece a little bit more. I'll give you a teaser on const expr coming up here. And yes, somebody just mentioned const expr, so my audience knows this is the right crowd. So, the experimental results for this example, again, I measured it, and it's not much. In this particular example, it's not faster at all here. But I think this example is just so small, there might be some noise here. But there are some other things. Again, this is where the story gets messy, and where we have to measure and try to understand what's going on. Is, again, if I'm putting something in memory, it might actually be more costly to do that memory fetch than to just recompute something. So again, this is where the story always gets muddled when it's, I'd love to have these neat tricks that I could show you that work every time. But, sometimes a memory lookup is going to be more expensive than just doing a simple arithmetic. Okay. So again, something that we need to think about here. Okay. Let's see. And someone's asking about hot reloading as it detects what's being repeated. I'll have to maybe follow up with that one later. All right, so let's look at just some other structural things that we can do with our loops. And again, these are things that maybe you're doing in your code, they add a little bit of complexity, but oftentimes can give you a performance boost. So here's a simple function here called index of, where I'm searching through the string, looking for some particular character, and I need to know the size of the string. And this is very C code here. But let's say if I find the character that I'm looking for, I return the index, right? I'm just trying to return some index, of this character that exists here, and then return it. But we could actually probably improve this, right? If I just go ahead and do a early return here. If I say, well, as soon as I find the index, because I just maybe need the first one, then just return here. Don't loop through the entirety of the string here. So again, another example that sort of makes sense of what we could do here to save some time. All right. So some other things that we could do here is, and someone's asking, is it okay return multiple times? So this is getting into a little bit of the, structure of our rules, right? Some folks will say, right, having multiple returns in a function is, a little bit of a code smell because it does increase the complexity, right? We need to think about the different logic in this particular code. When it comes to performance, for this particular example, which is probably simple enough, it's probably okay. I mean, I would be probably okay with something like this. Maybe it's a little bit cleaner to just set the index and then break. Again, if we want to follow that a little bit more strict. Yeah, someone mentioned just using break. So that would be okay. Yep. Yeah, couple ways to do this. All right. So another optimization we have, again, thinking about our loops, because this is where we're spending time doing a lot of computation, is this idea that we can unroll our loop. Okay, so what does this mean? Well, let's just say I have some array here of 4 elements, and I want to, compute some sum of all the elements in the array and add them together here. Okay, so this is equivalent to doing what I'm doing at line 13, right? Summing up each and every one of the elements here. So let's go ahead and, generally this is something that a compiler might do for you, might be able to do for you. It's actually a very powerful optimization, but what it can translate our code into, or you could do manually, is something like this, right? We transform this loop at line 9 through 9, 10, 11 here to something like this, 13, 14, 15, 16. And what we're basically doing is increasing how much we're incrementing our counting variable here, and actually just doing the steps one after the other. What does this save us? Well, we're not testing this condition as often, we're not incrementing as many times, and our code becomes very predictable because if our architecture is able to just look ahead, right, and not worry about branching somewhere else and jumping around, it's doing less jumping around. So again, this can be a very powerful optimization. And this is also an example where sometimes when you enable one optimization, something like where you identify this pattern and say, well, could I unroll this loop? Maybe then you say, well, maybe I could do something like a single instruction multiple data. This looks like I might be able to do something in parallel, summing a bunch of values. Maybe there's some way to do that. Okay, so we can kind of open our eyes up sometimes if we can identify that situation. And someone is saying, yeah, is this less readable? Probably. This is probably less readable here. Now, I'll argue here that, again, if, as we write code, if we go and transform from something like this, from lines 9 to 11 down to 13 and 16, that might, again, if this is a really critical performant part of our code, open us up to some sort of SIMD optimization. And we are making some trade-off versus what's going to be readable and maybe performant. Okay, that is part of this here. And it also just depends on experience, what domain we're working on, if these things are common, because there is a right place to write SIMD instructions. I mean, and maybe we might also argue like, hey, if we identify this situation, right, this is where we want to use a library like OpenMP or these types of things, or the standard library is going to have some parallelization stuff as well here. Okay, but we first have to just identify this pattern that it is available. Okay, so some other fun things, loop fusion. Now this one might be one your compiler might do for you. I think it's less obvious, but if we're iterating through a collection of data, any container, say in C++, and uh, going through all 300 elements or something, and doing something, and then we have some independent data set we're also iterating through an equal number of elements. This often happens, say in a game, say you have 300 characters or something here, and you're iterating through all of one part of their ecosystem. Right, you could maybe combine this part and get something like this bottom loop down here. Okay. All right. All right. So there are some other things. Again, I didn't want to talk too much about bit hacks, but I mentioned a few here. Some of these are math properties. Some of these are things you might have, learned. But there is this idea of strength reduction, right? There's common ones like plus plus I versus I plus plus that might make your code a little bit fewer instructions. And as somebody mentioned in the chat, the way to know is to actually take some of these and put them in Compiler Explorer on godbolt.org, and to actually see, do you get less instructions? Okay. Some other things that we can do here for modifying our code structure. Again, I do a lot of sort of game programming, so that's why these examples sort of come up here. But you might have this problem where you're trying to see if two circles here are intersecting. And that usually means that you're checking, well, if the distance between these circles is less than their radiuses, then they must be intersecting. But I can actually rewrite this code as doing a check first on the x's, a check first on the y's, and then performing my actual collision test here. So what am I doing here? I'm just trying to watch the questions here. What this is doing is it's just giving me a chance to do that fast exit. Okay, so similar to what we were doing with our little search problem with the index of operation, if most of the time we might determine that collisions aren't happening between this circle or they're overlapping, then we want to give ourselves a fast exit. Okay, so this is another pattern that we can use. All right, so a few other things here where we can modify our code using inlining, and this is actually an important part of C++ that we might use here, is generally we can basically take something, and let's go ahead and take a look at this example where I have these two functions, add and subtract, and then you'll observe that the maybe subtract function here is just calling add, and all add is doing x plus y here. So we can actually embed this operation or the body of this code here, add, into subtract here, right? And then we could further optimize it down to ultimately x minus y here. Now this is a little bit of a silly example, but what we've effectively done is eliminated a function call. What does that do? That eliminates these temporary variables that we have to place on the stack. And oftentimes, because we have more code now to work with here, x minus y, although this example is really tiny, but we've inlined or grouped more code together, that might enable further optimizations and further patterns that we can see because we've got sort of more code to work with in a block. And this is something that our compiler is usually pretty good at with inlining, and something that we probably want to rely on our compiler to do for us. As far as the actual inlining, this is the one that we probably won't do manually. Usually put the inline keyword in front of the function, and that's a strong, well, I guess it varies, but it's a suggestion to the compiler that you could probably inline this, okay? And for those of you who might be more advanced in this stuff, right, you can do like, if you're using GCC, force inline and these types of things if you really think this should happen, okay? All right, so there's some other little things that your compiler will often take care of here. If you have some expression like this, x equals 3, y equals x plus 4, well, let's just go ahead and do the substitution, okay? Just plug 3 in here and evaluate it at compile time, okay? And this is getting exactly to const expr, which someone mentioned, and I'll show later. But this idea of constant propagation, right? Just solve and reduce the problem. We don't need to do this extra instruction at runtime, okay? Just go ahead and put 7 in that value. Okay, so I've got all sorts of rules like this. Here's const for example. And this extends out to functions, of course. So you can, again, make the strong suggestion of the compiler to see that, can we try to evaluate this expression at compile time so that we're not spending any actual runtime when a user runs our program to compute this value here. And that itself was another one of the great trade-offs of C++. I've given some other talks about it. Other folks have given wonderful talks about const expr, but that we are able to actually make this trade-off of not just space and time in C++, but compile time versus runtime. So that's actually a very important thing, I think, or a very important reason to use a compiled language, because you might have that opportunity to, again, improve the generated code that you have. All right. And someone's got a comment here about, inlining. They say inlining willy-nilly will hit your instruction cache performance. Yeah, potentially, right? You are putting a lot of instructions together. And that can certainly be true. Right, we have to measure. All right, some folks are ready to measure. That's a great segue, I think, to a little case study here. So I've put together just a little example here with, say, a vec3 class. So this would be 3 floating point values, or maybe 3 integer values, the sort of mathematical type here. And let's just take a look at some of these optimizations here. So here's an example class here. Again, actually, I'll generalize it to just vec(n), so we can have any number of components in it. So it's an n element vector. Okay, very similar. I suppose we could just say standard vector. In fact, that's the type that we're going to use inside of this structure here to store a bunch of our components. Okay, so here's our name of our structure, vec(n). You can take in any type of data. So maybe we want to work with floats, ints, whatever it might be. And we'll store those components here and maybe perform some operations. Right, so we'll figure out how big is this structure. We can print it out, and maybe we can add 2 vectors together. Okay, so that's going to be what we have here. So let's look at one of these strategies, one of the first ones that we looked at, which is this idea of caching. Okay, so another runtime space versus runtime trade-off here. And I've gone ahead and implemented these 3 member functions for this vec(n) here. Okay, so when we initialize our data structure here, maybe we just do something here like we push back all the elements in a loop. Okay, so we determine how big is our collection, push back the elements. We want to print them out. We loop through for however components are in our data structure. Right, and components is a standard vector, so we have dot size, and then we can look at all of the components. And then for the addition of one vector to another, right, I'm using operator overloading here, so operator plus equals, and we'll take in some other vector and add each of those vectors together. Okay, so that's the idea. 3 relatively simple member operations here. So I want to optimize this, and well, can anybody, and I'll take an interactive audience answer here. Can anyone see where I'm recomputing work frequently? So I can kind of go back in our memory and try to recall some of our previous examples. Where does it look like I'm just recomputing something over and over and over and over again on this example? It could be in one function or multiple of them. What do folks see here? Yeah, folks are saying, a couple of things here. Yeah, so there's one for folks are saying the for loop and pointing specifically to size. Someone's pointing at the at, which is interesting, because that we could probably optimize as well. But yeah, components.size. Let's take a look at that one first here. There is going to be other stuff that we can actually improve as well. But I am actually calling this .size function over and over and over again. So this in particular, this could be potentially an expensive operation. Now, for our vector type, this is perhaps just storing some integer that it's returning. So maybe it's not that costly. In fact, maybe it gets inlined in some sort of way, so we're just accessing the member. So maybe that's not that big of a deal. But what if this is some sort of big data structure? What if this is a graph traversal? Okay, so we have to be able to sort of identify some of these things and say, well, just putting our performance hats on, am I recomputing something here that could be potentially expensive? If someone is saying, yeah, isn't dot size constant time? Yeah, I believe it is here for vector. So, I mean, let's just try to make this adjustment here and see if we actually get some performance here, okay? By actually caching our result here so we don't have to call dot size. Because again, maybe we're thinking about, well, not having to recompute the size of this components here. And that probably makes sense, right? If we're just printing off the vector that we're not recomputing the size. We're assuming this thing maybe isn't growing, right? We've said that this is a const type of print function. So let's go ahead and see, does this give us some performance. But again, my caveat here is if we're going to change this data structure later, maybe to a list or something, we want it to be more dynamic, or maybe this is a graph or something. This is just something that we should identify potentially with this data structure, okay? And someone's also giving us suggestions saying, wouldn't iterators be better here? Well, yeah, potentially, actually. This is, with an iterator, we might actually save, since we're just incrementing a pointer. So maybe if we used a range-based for loop here, which is just iterators, when we're accessing our array, right, that's usually a multiply and add, right, versus just our iterator where we're just directly accessing the value. So it might be a little bit more performant, okay? So to Vivek asking that question, that certainly could be. Yeah, so another thing we got to measure and think about here. All right, so let's talk about that. Because right now it's just speculation, right? I'm saying, hey, this sounds like a good idea. And some of you folks are poking and saying, well, actually, I think that's constant size and all these sorts of things. So we have to learn how to measure a little bit here. So how could I measure this? Well, again, if we don't know, maybe the first thing that we're going to try to do is run a program like time. If you're on Linux, maybe you have some other tool on Mac or Windows to just see, what's the overall time to run this program, okay, where we're doing some work here. So the overall runtime. Okay, and I can tell you this program's just adding, I think, 1 million or something iterations of add here. Okay, so with no optimizations, it takes 0.025 seconds. With the caching, maybe it's a little bit faster. This example, maybe it's too small. Maybe we need to do more, 10 million iterations, 100 times throughout the day and get a distribution. But there does seem to be some effect here. Okay, but I'm not convinced. It might just be noise in our data, meaning like this doesn't seem significant enough quite yet. Okay, so let's see if we can try to tease out some more information here. Maybe from a profile, or a better profile that'll actually give us some information. So a tool like perf on Linux is a great one. Mac has tools, Windows has tools. Whatever platform you're using should have some tools, but I like perf here because it'll give us a little bit more of a detail about how much time we're spending and maybe why we're getting the actual performance we're getting. So with that in mind, if I actually run this here, and we see with no optimizations for our program here, again, this was our original code, we get a box that I've highlighted here, highlighting our performance. So about 20.91 milliseconds. Okay, that's sort of the key number here. And then our refactor here, we get at 18.78 seconds here. Okay, so again, maybe it's a little bit faster, but we can try to understand why. Okay, well, we see maybe some of these things like the number of cycles, so maybe the instructions is a little bit less. The actual, instructions here and choice of instruction. Fewer branches, so maybe there were less comparisons here. But there are a lot of branch misses here, which is interesting because maybe we are doing that memory fetch or something, and that isn't, that's costing us something here. So again, we're getting some results. We can actually start to analyze this now and see if our pattern, some of these, strategies work. Okay. So if we dive a little bit further into this with a tool like perf, we should actually try again to see the full story. So, rather than just looking at the overall program, let's try to see within the operations how much time I'm spending. So here's an example. Again, on the top image here, this is our non-optimized program. And what I'm looking at here is how much time I'm spending in the program here. So, 39.14%, for example, in this plus equal operation. Okay, that's where we're spending a lot of time. 30.17%, we're doing this size check here. That's how much time it's spending to make that function call. And in the caching version here, which we can see, where we effectively eliminated that size call. In fact, you'll see it only shows up a few times here. Maybe internally it's called. We are spending 54% of our time doing our additions of the overall program runtime, that is, and 15% doing other stuff. So interestingly, again, at first glance, if you look at this, you're going to say, well, now I'm really concerned. I've slowed down our program or something. But no, again, remember, this is just where we're spending our time within the actual relative runtime of the program here. Okay, we sort of want to look at both of these operations, the one that we are doing, plus equals and size, and have some idea of how much time we're spending here. Okay, so it looks like we are saving a little bit of time there. Okay, that appears to be where we're potentially getting some savings here. Okay, it's still a little bit too small to be 100% confident here. But it is digging a little bit deeper into this problem, so we can actually see and measure the sort of total operation. And there are lots of tools. Some folks have mentioned some tools in the chat here that can give you the sort of detailed call tree, so you can actually see, okay, within plus equal, how much time am I spending? So there's lots of great tools like that. Kcache grind's a good one, flame graphs, to name a few other neat profilers. Okay, so again, now was caching a win? Maybe not a huge win, but there appears to be some sort of performance boost, but it's really small and it's still kind of noisy. So I mean, let's try something else. Let's try to look for some other strategies here. So let's think about compile time computation. Okay, let's think about if I can do something more at compile time here. Okay. So ultimately, again, we're always trading time and space for performance. But again, as I mentioned in C++, we can change runtime computation for compile time in some cases. So taking a little bit more time to compute on our side as developer often can be a win for the user if we save them time. So what can I do here? Well, if I specify this problem a little bit more clearly, I could actually say, well, this vector, maybe its length isn't changing, or maybe I can at least initialize it with an initial length here. Okay, and then I could always maybe grow it later. But what if I actually passed in length here? Okay, so here's the change. Here's our original data structure on the top right. But now I'm going to pass in a template argument for the length here. Okay, so that I know for this vector of type t, when I'm initializing it, I can actually simplify our constructor a little bit and just take in the actual length. Okay, so we can push this a little bit further. And now if I actually run this, this does in fact improve our performance. Where did it improve it? Well, a little bit in the allocation here, or rather I should say, I'll get to the allocation part in a moment, but I don't need to check for vector.size because it's fixed based off of this length here. Okay, now again, I've changed the shape of the problem a little bit, but if I'm using these, say, as vector 3s or whatever type you might want to use, and a length's not changing, just make it something that's known at compile time. Okay, so this makes it faster. All right, so we've got to solve the right problem with the right data structure. And we're approaching that here with some of our thinking about our space versus time trade-offs here. But let's think about that more, because we've changed the shape of the problem, right? We've specified something clearly, right? And this is getting back to Knuth, right? Saying not to make optimizations too soon until you've measured and you actually know the shape of the problem that you're trying to solve. That's really important. So all that complexity that we introduced into our code, we don't want to introduce more complexity if it's going to be a problem that's changing, for instance. Okay. All right. And my camera keeps turning off. But let's think about again, do I need the capabilities of the vector? Well, I have to be careful again because I've changed the problem, but if it is just a static size, well, then I can just actually allocate it on the stack here, right? This can just be a fixed size uh, array effectively. Okay, I can have the type here and the number of components, and the size is known here. So oftentimes, again, the best data structure is going to win when it comes to optimization. So, again, regardless of the little tricks and tips that I show you, it's often just best to solve the right problem with the right tools, thinking about your time and your space. So let's go ahead and take a look at this one here and see how fast it is. Okay, so if I solve the same problem, iterating through and adding two vectors together, now we're down to 6 seconds here, 6 milliseconds here. Okay, so amazing. We're getting much better here, much better performance, and that's pretty cool here. So now that we've constrained our problem a little bit, we can see the performance improved a lot more. Right, we're solving a specific issue. So again, and if switching to an array felt like cheating here, I did go back to this example and I tried it by just saying, well, let's make it an array. Let's get rid of all the vector stuff and just make it a heap allocated array. The results were still noisy because what we're really paying for is memory accesses on the heap and the allocation. But it still was a little bit, a little bit better, but the best is still the stack allocated array. Okay, so in general, just a pure array without any overhead. And again, I have to mention, we should probably be using standard : array, right? That's what we want to use here. But again, here's an example of a heap allocated array. But anyways, where this is pushing us towards here. And someone's asking, just to be clear here, if I'm profiling, yeah, I am using an integer type here. So 4 bytes of data here is what I'm doing. And then again, that's going to maybe change, right? If we're doing floats, are we doing divisions of integers versus divisions of floats, right? So we're going to get different results here. But that's actually a nice segue, right, into thinking about, well, what's the type here? And that gets us into this optimization strategy or pattern on specialization, right? What if we are worried about, oh, I'm working with, this large object or integers or floats, right? And then again, you've heard the mystique of, maybe it's more expensive to divide an integer than a float and some of these things, but now you can actually test them, right? Maybe do an experiment. So let's look at specialization here. And one of the things that we can actually do is for this function here, operator plus equal, because, well, why am I choosing this function? Actually, let me go back here and show you. Well, if I go back to my profile, I'm spending almost 80% of my time here. So maybe, again, we want to do that similar deep dive, looking at this program and saying, can I make this faster in my program? So I'm spending less relative time there. Okay. So what I can do here is, again, provide a template specialization here for this member function. And what I'm going to actually do here is tune this a little bit here. So what I'm going to actually say is, and let me go ahead and give you the specialization, is if I have vectors of size 3, so something that's kind of a known small quantity, right? You would use these in games or scientific applications, right? If you have an X, Y, and a Z and are trying to represent some geometry, right? No need to have this loop because we learned that was one of the things that our compiler might do for us, this unrolling process. Let's just go ahead and have the specialization down here and add in each of the components individually. Okay, right? It becomes very predictable for our architectures to see what's going on. So we like this. Let's go ahead and try this. I do run this here, and it looks like in our relative program, it's reduced how much time we've spent here. Okay. On the overall runtime here, our specialization with the array, and I did this test as well with just using a vector, this is our best one yet. Okay, so now we're down to like 0.006 seconds here. Okay, so we're getting even better and better and better here. Okay. So, what we're getting to here is, our code layouts changed a little bit. We've provided some optimizations here, and we've thought a little bit about, problems that we're trying to solve. Okay. All right. So just one more pattern here, and then I'll start wrapping up with some final thoughts on this. But some other things that we can do that are kind of interesting are multi-stage setup for our objects. Now, again, this is complicating our code a little bit, but again, if we sort of know what problem we're trying to solve, let's go ahead and say, well, you have to go back to that vector example and say, well, we do want to be able to resize the vectors. We do actually have operations for dot resize, so we can do an allocation very quick. Okay, so these are some things that we want to keep in mind. And then we could fill it. And there's clever ways you could use like a mem set if all the values are the same and so on to get rid of this loop. But just a few ideas there. So wrapping up the vector example here, we've played around with some strategies based off of what we've learned from Bentley's rules, or really what are just time-old optimization strategies. So things like caching, compile time optimization, specialization, using the right data structure, and maybe even multiple phase initialization. Okay, and hopefully we've learned just a little bit about how to profile and investigate these strategies. Because again, I want to be careful about giving a concrete pattern or anything, but these are just sort of known strategies that may or may not help us, and but we have to measure. So there are more patterns and strategies that exist. This certainly aren't all of them, and you'll find these across the C++ standard template library, for instance. Things like hinting, right? You can provide little hints in various algorithms to help improve the performance. So that might be something you can take a look at. We've got precomputation, again, const expert, doing things with templates you can do a lot of work in. For example, to speed this up, we've got lazy versus eager evaluation with stood async. Lazy evaluation, meaning don't compute something until you actually need the value. Things like copy on write fall into this category. Short circuit evaluation all fall in this category. Again, if you're a graphics person like me, you do batch operations, so many things at once, and try to organize your program logically, again, with the code structure. And there's other things like hashing, which again are just sort of clever spending upfront time, say, to hash a string, convert it into an integer. And then if you're comparing lots of strings, it's maybe faster to just compare those integers. So those are just some strategies there. Now, again, I'll give an anecdote here and kind of end with performance is tricky, but it's fun. Hopefully we've learned it's fun today. A fun anecdote that I heard in the sort of lore of optimization, or my compiler does this sort of things, is, there was a paper a while ago that said that if you add a random printf in your code, could be C or C++, you could get a 10% performance change. Well, the reality was adding that print-off shifted things just enough in the code that sometimes you got better results based off of where the memory was laid out. So just some fun, notes there. So again, these things exist in the lore. Fun. Optimization itself is fun. I really love doing it, and it comes with many trade-offs and strategies. So you have to measure. And I'm going to give you some homework here in a second. And that's going to be, well, what I started off with at the start of the talk, to actually go and read this paper by Donald Knuth. So then you can tell your friends, family, and other CppIndiaCon members that, yeah, you've read the paper and you know where this comes from. So with that said, I'll go ahead and end it. I think we're close to time. And then just thank everybody again.